So here we find ourselves in section 4.3, and they're going to quickly look at the tangent and cotangent functions, have us just investigate those for a while. Tangent and cotangent are interesting. They have a period that's only pi, and we need only to determine the graph over some interval of length pi. And so the rest of the graph will consist of repetitions of that. And so the tangent function is not defined at any of the pi over 2's, right? It's sine over cosine, and cosine of pi over 2 or odd pi over 2 angles are going to be 0. And so it's undefined there. What you'll know, I was going to say remember, but I think it comes across more in a pre-calc class, which is next. You're going to find out anytime that we have something be undefined, there's an asymptote there. So I'm going to come in here in red, and I'm going to put some marks right here. That mark and this mark are at pi over 2 and negative pi over 2 respectively. Those are where the function is absolutely undefined. Okay, it's also going to be undefined at 3 pi over 2. And at, over here, negative 3 pi over 2. Now we just need to have 1 in there. So let me go back to the black. You know tangent of 0 is 0. Tangent of pi over 4 is 1. We know that, right? Pi over 4 is 1. Negative pi over 4 is negative 1. Just going through what we know. And what we want you to see is that as you get closer and closer to pi over 2, you get huge. That's what happens around asymptotes. You get big and get big quick. And so that's what we have. If you remember in the end of chapter 7, we were saying, hey, there's no angle that could have a sine of 1.4, so there's no triangle that's possible. We can't say that with tangent. Tangent can have every single number as an output. Tangent's output is all reals. And so what happens is, here at pi, which is right in between there, we're 0, and the thing just repeats itself. That's what that wording above was trying to say. So here at negative pi, right, we would look the same. And it just is repetitive over and over and over again. We need a fundamental understanding of these graphs in order for their inverses to make sense, and so that's why they harp on the graphs so much. So the domain of tangent is all reals. You can take the tangent of any angle you want. The range is also all reals. The tangent function is an odd function. And that means that tangent of negative x is equal to the negative tan of x for all x. They may use that in the future. But that's an odd function. It's definitely not symmetric about the y-axis, but it is symmetric about the origin. Okay. There's functions that are neither even nor odd, though, as you probably know already. The tangent function is periodic with the period of pi. Its x-intercepts occur at all the multiples of pi. Y-intercept is 0, 0, and it has these vertical asymptotes, lines that it can't cross, at pi over 2, negative pi over 2, 3 pi over 2, essentially any n pi over 2 where n is an odd integer. Okay. So what would the graph of tangent 2x look like? Now remember what the 2 does. The 2 is an amplitude adjustment. So this is not going to do much from our perspective. Here's minus pi over 2, and we'll just show that one period. It's very typical to only show one period. So this is minus pi over 2 to pi over 2, still going from a period of pi. There's been no period adjustment. Okay. And then we're still going up to infinity there, but now when you plug in pi over 4, you get 2 out. So essentially what happens is it just gets steeper quicker. Okay, it just kind of stretches out for a little bit. Sometimes books will call it that. They'll call it a vertical stretch, right? And then what's happening here? Well, there's a period adjustment and an amplitude adjustment. So we'll come in here. But there's no phase shift, but there is a period adjustment. So this thing is going to have a new period. What's its new period? Its old period was pi, but now we're going to divide that by 2. So now its full period is pi over 2, which means, take a look at what happens here, because I can show it this way. It means that my asymptotes is still going to go through 0, 0. My asymptotes are at, oops, let me keep them in red, minus pi over 4 to pi over 4. That has a distance of pi over 2. And so basically those asymptotes got swung in by half. So a cool way to think about that, still going through that point. Now remember the negative. The negative means I'm going to flip it. So now I'm going down very quickly to this guy and up very quickly to that. Not because they're close, but because of that 3. Right? I think there's a little factor in both in there. And so if I add pi over 2 to pi over 4, I'm going to go out to 3 pi over 4. And so let me show you something here. Actually, let me stay here one. Put a dot right there. And then come in here and put a line on this other side. That's got to be pi over 2 later. That's 3 pi over 4. Right? Because pi over 2 is 2 pi over 4. And so we're going to be there, and we're going to look exactly the same. So you're going to get a bunch of these in there, right? Now notice they look a little bit different, but just try to draw them as much as you can the same. You're not going to lose points for style points. And so what would cotangent look like? Easy. Remember cotangents issues. Cotangents issues are where sine's 0, because that's what's on the bottom. So it actually has issues at 0 and at pi. So that's pi. And it's going to have an issue at 2 pi. And it's going to have an issue at negative pi. And at pi over 2, it's going to be 0. And remember, it's positive in the first quadrant. This is pi over 2 right here. Angles between 0 and pi over 2 in your first quadrant, so it's starting high, falling through this middle point and going low. And it just follows that same pattern coming down. So cotangent's just as nice. Cotangent falls as you look at it from left to right, but it makes sense when you talk about what has to be happening in that first quadrant. So the cotangent function has vertical asymptotes everywhere it's undefined, and that is when sine's 0. So on 0 to pi, it has vertical asymptotes at 0, pi, 2 pi, negative pi, essentially any multiple of pi, where n is an integer. Including 0, right? 0 is an integer, so I didn't need to say that. And then they'll have us graph. Okay, they'll have us do some shifting and things, and we go through pretty much the same type of setting that's happening here. So like if we look at this example 2 that's here, 1 minus 1/2 tangent 2x. So let me just draw my axes and we'll decide what needs to stay and what needs to go. Okay, period. Period is now pi over 2. Was pi, right, for tangent, now it's over 2. So when I draw my asymptotes in, they're going to be, whoops, went to the eraser for some reason. They're going to be at minus pi over 4 and pi over 4. Right? And I don't know how many they want us to graph. So this would be 3 pi over 4. Okay, all those will be places where it's undefined, and they go out infinitely long. We know that a negative out in front of the tangent means it's going to flip. We knew in the center it's going through 0. And it's going to flip. That means it's going to go negative down here. And it's going to have a 1/2, so it's not going to fall as sharply. It's going to hug that line a little bit more and then quickly go That's what the 1/2 will do. It will make it hug that x-axis a little bit longer than it normally would have. Okay, and so it looks like a cotangent, but it's not. The reason why it looks like a cotangent is because it is it's falling, but it's falling only because of this negative that's out in front. Awesome. Now the whole thing needs to be shifted up one full unit. So if I'm going to shift it up one full unit, all I need to do is take that line that I originally drew as my x-axis and move it down one unit so that those points that I referenced everything off of go there. Now you can tell that this is a tangent because it goes through 0, 0. Tangent will go through 0, 0. Cotangent will not. Cotangent has a problem at 0. So if we go look at this next one, again, my recommendation is to just draw it. And so what's the worry about the -1 next? No period adjustment, it's still pi. We know that it has a problem at 0, and then it's also going to have a problem at pi. It's going to cross right in the middle of that, and it falls, and the 2 is just going to make it go up a lot steeper. Okay, it's very imperceptible when you see it by itself. Now, what's the -1 going to do? The -1 is going to drop it 1 unit. If I want to drop this thing 1 unit, then I just have to move the x-axis up 1 unit so that that point that was on the x-axis is now 1 below, and everything's set. That's my recommendation. Lots of pencil work so that you can readjust in there. The pencil should come across. My experience is that it's just fine coming across in pictures that you take of your work. And we do a very similar thing for the last one there. So properties of the cotangent function, its domain is -infinity to infinity. Its range is also -infinity to infinity. You know what? I made a mistake. Its domain's not that. Its domain is all reals, with the exception of taking out n pi, where n is an integer. Sorry about that. I was going to make a mistake, and I think I made a mistake with the tangent one. We'll go back. We can't, n pi's are not part of the domain. That's why they have vertical asymptotes at all those points. And so the cotangent function is an even function. And so cotangent x coming through. So it is even as you go through. Or is it even? I don't know why I said that. Let's take a look. Would it be mirrored? Let's go back and look at the original cotangent function. Is it mirrored around the x-axis? Does it look exactly the same? Could I flip it over on itself? And I don't think that we can. I think that this is also an odd function. Okay, I apologize for saying that it was even so quickly. I think it's still odd. It's an odd function. So that's negative cotangent x. Its period is pi. It's got x-intercepts at the pi over 2's. The odd pi is over 2's. The y-intercept is none. Can't cross the y-axis because it has a vertical asymptote there. So we do need to come back up, and really happy that that drove in my memory, and I'm sorry for those that were upset that I like, hey Jensen, you're wrong about that. The domain for tangent is all reals, but you need to take out all the n pi over 2's where n is an odd integer. Right? You can't have those places where it's undefined be part of its domain. Don't know why I didn't think about that before. I certainly was thinking about it here. If c is any number, how many solutions does the equation c equals tan x have in the interval from negative 2 pi to 2 pi? Well, let's talk about that. From negative 2 pi to 2 pi. Well, what's the period? The period is 5. Oh, sorry, the period is 5. I don't know where I got 5 from. The period is pi. So how many pi's are there as we go from negative 2 pi to 2 pi? So as you go from negative 2 pi to 2 pi, there's 1, 2, 3, 4. There's going to be 4 answers because you covered a 4 pi period coming through there. You could see it on the graph, but just intuitively knowing what the period is, you can get that. So see how they're saying assume no phase shifts? That's very typical. Otherwise, you would not be able to tell the difference between a tangent and a cotangent. They want us to talk about what this is. So I would look at this and realize, ooh, this thing's got asymptotes at 0 and pi. This is a cotangent. Cotangent falls, but this is rising, so this is a negative cotangent of x. I'd look at B and say, okay, it's got asymptotes at pi over 2. Okay, so if it's got asymptotes at pi over 2, well, let me look here. Actually, it's got an asymptote at 0. Okay, that's what I should have paid more attention to. It's a cotangent. And let me put y equals cotangent. I'm not sure what the, oh yeah, because it says write a function. Well, if I'm going to write a function, maybe I should put it in function notation. Maybe I'll say f of x is equal to that, and f of x is equal to, this I think is a cotangent function. Its period is now pi over 2. Now why did I call it cotangent? At first I saw the pi over 2 thing and I got a little bit too excited. 0 is still an asymptote. And so this is something that got cut down from a period of pi to a period of pi over 2. That means this is 2x in here. As we look at this guy, going through 0, 0, this is tangent. Period does look like it is pi. But let's take a look at something. It's falling, so it's negative. It's definitely tangent. Do they give us enough information to know whether it's a 2 or 1? So halfway through, I should be at 1. And halfway through, tangent of pi over 4, I'm down to 4. So this, I think, is minus 4 tangent x. Does that make sense? So this is pi over 4. Pi over 4 normally would give me a 1. But now it's giving me a 4. So I think that's where they're going to argue that that's minus 4. And then what's this one? Oh, it's a cotangent. Again, potentially. Let's see. It's got an asymptote. It looks like it's got an asymptote at 0. And it's got a strength of pi over 2. It's not much different than this guy right above it, with the exception, well, so it's cotangent, maybe. Be negative if it was a cotangent because it's going up. And its period's cut in half. So f of x is equal to negative. So I think it's cotangent because it's got that 0 asymptote. Tangent wouldn't. If I plug in 0, cotangent of 0 is undefined. That's good. That's what's happening there. If I plug in pi over 2, that's going to give me pi. Perfect. So that seems like the right one there. And then this last one is definitely a tangent because it's going through 0, 0. Its period is what? So sometimes to get the period, I just look at how many times it's going through in a single period. So a single period, so it looks like it's happening 3 times in a single period. So this is tangent of 3x. And that's what our f of x is going there. So try not to get too tricky when it comes to the exams, but that's what we have. In the future, we'll be looking at secant and cosecant graphs. They're essentially just built right off of tangent and, off of sine and cosine. So not going to be bad at all as an extension there. So good luck with the graphs. Let me know what questions arise as they come up.